Okay, so what I want to do here today is to pose a question, which is, when does a quantum dissipative evolution mix rapidly? And hopefully in the next 25 minutes, I will give you some partial solution to this question, at least in the particular case we are interested in. Okay, so I'm assuming that in general, people here might not be familiar with everything that is appearing in this question, so I will go like word by word and explain what I'm mentioning here. First of all, since we want to answer when does a quantum dissipative evolution mix rapidly, I want to say what I understand by a quantum dissipative evolution. And by that, well, let me clarify that, of course, we are studying open quantum many-body systems, because we know that if we want to perform a realistic experiment, then it cannot be completely shielded from noise. This is why we want to assume that we have a system. We have a system that is contained in a certain environment with which it interacts. And therefore, if we assume that the system has some initial properties, some initial energy, with time the energy is going to tend to dissipate. So we are going to have some dissipative system. And what we are interested in here is some particular systems and some particular relation between our system and our environment. Why? Because in general, this is a mathematically very difficult tractable problem. So if we assume some conditions on the environment, we can simplify the whole mathematical setup, and then we have some tools to tackle this problem. In particular, we assume that the coupling between the system and the environment is weak, in the sense that the environment is much bigger than the system, right? So that what the system does to the environment is essentially negligible. And also we assume that the environment does not hold any memory of what happens in the past. So this is why we are assuming some Markovianity, and therefore our quantum dissipative evolutions are just being something that is called quantum Markov semigroups. And these quantum Markov semigroups are just semigroups of maps which are quantum channels. So all these maps are completely positive and trace preserving. We are defining them over the sets of density matrices in a certain finite dimensional Hilbert space. And because of having a semigroup, we have these two fundamental properties that define a semigroup. So essentially, at instance 0, the map is given by the identity. And when we compose the maps at instance t and s, we just get the map at instant t plus s. And since we are in finite dimensions and everything, we know that there's a generator, such that if we differentiate the elements of our semigroup with respect to time, then this generator, this is equal to having this generator composed in the right side and in the left side with our map at instant t. And this is the so-called master equation. So this generator, because of satisfying this equality, is usually called the Liouvillean. And also because of the particular form that a setting satisfies, it's also called the Liouvillean. And the important thing that I want you to take from here is that every element of our semigroup can be written as the exponential with time of our generator. With the generator, I'm not going to go into concrete details of its form, but I just want to tell you that it can be written as something like this, where here, this is just the Hamiltonian in the system, and these are just some terms that model how the system interacts with the path, as most of you probably know. Okay. So I told you what I'm understanding as a quantum dissipative evolution, which are just these quantum Markov semigroups. And now I can explain you what I understand by mix. And by mix, I'm just talking about the convergence of the semigroup. So for me, mixing is just studying the convergence. And in general, when we have a system and we have a heat bath and the system has some initial energy or some initial temperature, for example, because we're just going to study thermal evolutions, and we let it evolve with time, in general, this doesn't need to converge to some thermal equilibrium. But for this to converge, we need to assume some further conditions on the heat path. The first one of them is that we have a unique full rank state, which is going to be the thermal equilibrium. It's just going to be a Gibbs state, essentially. And then we need to assume that we have some reversibility, which is mathematically given by this expression here. But I don't want to go into a lot of details here. The only thing that I want you to know is that if we assume these two things, we have convergence guaranteed. Our system is going to mix always. So essentially, we are going to have an initial density matrix in our system, given by rho. We are going to let it evolve with time. So after a certain time t is going to be given by the exponential with time of the generator applied to our density matrix. And when we let time go into infinity, this is always going to converge to the thermal equilibrium, to this sigma that I'm taking here. And this sigma is going to be a Gibbs state of a local Hamiltonian. Okay, so we are going to have convergence always. So you might wonder, why were you asking in the question, when does a quantum dissipative evolution mix? So it mixes always in the cases that we're considering here. Yes, but I was adding something. I was adding the part rapidly, which is what we are interested in. So for that, what we are studying now is how fast does this convergence happen? And to study this speed of convergence, we need to introduce some new notion, well, that was introduced much before us, which is the mixing time of the semigroup, or the mixing time of the generator. And the mixing time is essentially, for a certain epsilon, is the first instant, such that if we take any initial density matrix and see its evolution after time t, then it has already fallen inside the ball of radius, the thermal, of center, the thermal equilibrium, and radius epsilon. So this is just the expression that I'm writing here. And once we define this mixing time, we can define what I mean by rapidly. And essentially, rapidly for me is that the mixing time converges well enough. It scales well enough. In the sense that we have rapid mixing, is the mixing time scales logarithmically with the size of lambda. Of what is the same? If any time that we consider an initial density matrix in our system and we study its evolution after a certain time t, the distance between between the thermal equilibrium and this evolved state is something that scales polynomially with the system size, with the size of lambda. Okay, so this is the regime that we are considering here. This is what we call rapid mixing. So I told you what a quantum dissipative evolution is for me, what mixing is, and what rapidly is. And now the next part of the question that I have to tell you, which is the important part, is the when part. But before going to that, which is the technical part of the talk, I want to tell you why, because this is like the selling part, why we're interested on these kind of results. And the thing is that quantum Markov semigroups in general model a lot of different interesting things that appear in various contexts in quantum information theory. But in particular, when we have rapid mixing, in a very simplified way, we can say that then we don't have error correction. And essentially, the idea is the following. If the mixing time scales logarithmically with n, now n for me is the size of lambda, then we don't have enough time to do error correction. Okay, so the information is being destroyed too fast. And for having some possibility for error correction, we would need at least the mixing time to scale polynomially with the system size. And even to have some self-correction and something that would be more useful for quantum memories, we would even need the mixing time to scale exponentially. So in a sense, our result is a no-go result for error correction. So if you have rapid mixing, then this is bad for error correction. But in a more positive way, as I said, quantum Markov semigroups model a lot of different features that appear in quantum information theory. In particular, they model many different kinds of noise. So there are many positive results and many further positive applications that we can obtain from these results, which have to do first with the robust and efficient preparation of topologically ordered phases of matter via dissipation. Of course, one can also talk about the possibility of classification of dissipative phases of matter, because if you have some mixing time which doesn't change in the whole line for the temperature, that means essentially that there's no dissipative phase transition. So this is a way to classify these guys here. And finally, as I'm writing here, the nice thing of having some mixing time that scales very slowly with the system size is that the states for which, the Gibbs states for which this happens are actually some states that can be efficiently sampled and efficiently prepared. So in particular, this can help us to design more efficient quantum error correcting codes by optimizing some noise models that have to do with some Markovian noise, sorry. Okay, it came back. Okay, so now I told you why we're interested in this kind of systems. So now I want to tell you when we have this feature, when our quantum dissipative evolutions mix rapidly. And for that is for what we use some strong mathematical tools, in some sense, which are these quantum logarithmic Sobolev inequalities. And to prove them, the main ingredient that we use are some results of quasi-factorization of the relative entropy. And the idea that we can do this is the following. So from now on, I'm just going to call these guys log Sobolev inequalities. What we do is take an initial density matrix in our lattice, and we take its evolution after a certain time t. And then we know by the master equation that differentiating this state at time t with respect to t is the same as just taking the generator evaluated in it. So we can just take the relative entropy between the evolved state and the thermal equilibrium, which is given by this expression here, and we can differentiate with respect to time. And if we do that, we just obtain this expression, because first we are differentiating this term, so we are getting this, and when we differentiate this term, we get something that is traceless, so it disappears. And the thing is that now, if we plot this relative entropy with respect to time, we get something like this. So we get something that is always larger than or equal to 0, but is convergent to 0 with time. And that means essentially that this is decreasing, but also the absolute value of the derivative is decreasing. So this gives us the possibility of writing a functional inequality, which is essentially an inequality between the relative entropy of the evolved state and the equilibrium, and minus its derivative. This is something that we can do. This is how we create a functional inequality. And of course, for every concrete row and for every instant of time, you can find an alpha such that this inequality is true. But the idea is that now you want to find a universal alpha such that this is always true. This is a log Sobolev inequality, and the optimal alpha such that this is always true is the log Sobolev constant. So the log Sobolev constant, or the MLSI constant of this generator, is defined just by taking the quotient between these guys, and just taking infimum over all possible density matrix of this quotient. And if you define it like this is how you obtain this log Sobolev constant. And then the only thing that is remaining to do now is to show you that having a log Sobolev constant implies rapid mixing. And this is why we want to obtain log Sobolev constants. And for that, what I do is go to this inequality, and I use Grunwald's lemma, for example, so I integrate it, and I get some decay rate for the evolved relative entropy with respect to the initial relative entropy and some exponential decay with time. And the rate of the exponential decay is given by this log Sobolev constant. So now, the only case in which we are interested is in which the infinite limit of these log Sobolev constants with an increasing family of lattices going to the thermodynamic limit, when this is positive. And when this is positive, and we can actually obtain an inequality of this form, we can further apply some other inequalities, which are also probably familiar to you, like Pinsker's inequality, for example. And then we have an upper bound for the one norm of the difference between the evolved state and the thermal equilibrium, given in terms of this guy here, which is just coming from this term. And then we evaluate the worst case scenario for the relative entropy, which is given by the logarithm of the inverse of the minimal eigenvalue of the thermal equilibrium. And in general, this might look a bit strange to you, so maybe you don't know why I want to have this term here. But what I can tell you now is that we have a thermal equilibrium for sigma, so we are all the time considering that sigma is a Gibbs state, which means in particular that the minimal eigenvalue is going to scale like the inverse of the exponential of the size of lambda. And then it means that if we replace this here, we have something that is poly with the size of lambda, which is just what appeared in the definition of rapid mixing. So that essentially tells us that if we have a positive MLSI, if we have an MLSI, then we have rapid mixing. And another important thing that I want to remark here is that this is something that one cannot drop very easily. Because if you consider something that is exponentially weaker with respect to the system size, which is just the spectral gap of the Lindbladian, you get a bound of this form, but then this bound, this term here, scales exponentially with the size of lambda, not polynomially. So this is not good enough for rapid mixing. Okay, so what I'm telling you here is essentially that the solution, the answer to this question of when does a quantum dissipative evolution mix rapidly is when our quantum dissipative evolution has a positive MLSI. This is sufficient for having rapid mixing. And this is something that is sufficient. We don't know if it's necessary, but what we know is that having a positive spectral gap is usually not enough. And this is something that can actually be summarized in this scheme that I present here. So essentially, we just said that this log Sobolev constant implies rapid mixing. I guess you can believe that this implies the exponentially weaker spectral gap that I was mentioning before. And this, in general, doesn't imply rapid mixing. And all these results, which are some properties which have to do with the dynamics of the semigroup, they can be related to some properties of exponential decay of correlations on the thermal equilibrium, on the Gibbs state, which is something that is a completely static property. So this is the power of this scheme. You can relate some dynamical properties, which have to do with the convergence of the semigroup, with some properties which only depend on how correlations decay on the Gibbs state. And you might be wondering here, if all these arrows are direct implications, then I have like a complete equivalence between all these properties. But the thing is that the box that I'm writing here contains a lot of different forms of decays of correlation. So this is why there's not an equivalence between all these different notions. But what I can mention very fast is that if we study different forms of correlations and decay of correlations between two spatially separated regions A and B, and we see how correlations decay for a Gibbs state of this form between these spatially separated regions, there are many different definitions that we can take to study these correlations. And in particular, if we take the usual operator correlation given by this expression, the mutual information, and something that we call the mixing condition, because in the for classical spin systems it's called a mixing condition, then you have this chain of inequalities. And what we can prove is actually that having some exponential decay in the so-called mixing condition is what implies having a positive log Sobolev. This is what we do in this project. And because of having this chain of inequalities, clearly if you have some form of decay of correlations for this one, you have it for the others. This is why we have these two arrows. And what can be seen is that having rapid mixing implies exponential decay in the mutual information. So what you see is that if we were able to reverse this arrow here, we would have like a complete cycle, and then we would be able to completely characterize rapid mixing in terms of having log Sobolev or not having it. Right now, we only have a no-go result, right, because we only have this arrow. But what would be interesting would be to be able to completely close the cycle and do the same for the spectral gap and for the exponential decay of operator correlation. Okay, so since I don't have a lot of time left, what I'm going to do now is to tell you this strategy that we have developed to prove positive MLSIs, how it is constructed. So first of all, we want to prove that there's some positivity for the MLSI. I mean, that given a certain generator, this quantity that I'm defining here is positive. And in general, this quantity, if you see, all the terms here depend on lambda, which means that it's very difficult that the infimum doesn't depend on anything related to lambda. So what we would like to have is that this limit can be bounded by something that depends on lambda but is positive. And this is something that usually is not going to happen. So in classical systems, what they do is to reduce these log Sobolev constants in the global lattice lambda to a sublattice A, and they pay some factor that only depends on the size of A. This is something that we cannot do in the quantum realm because of the correlations between A and the complement. But what we can do is to define something that is called a conditional log Sobolev constant from lambda to A, and then pay some price depending on the size of A, and prove that all of this is positive. And this is what we do in this strategy. So once we have, the first thing that we have to do is define this conditional log Sobolev constant, and this is something that we can do in this form. So we have a generator now that is always the sum of some local terms. And therefore, for defining the conditional MLSI constant in a subregion A of lambda, the only thing that you have to do is take here the terms of the sites that live in A, instead of taking all the terms in lambda, so the numerator is fine. And the denominator is a problem, because now you have to reduce the relative entropy in the global lattice lambda to some conditional relative entropy in A, which means that for every particular case, you will have to define some conditional relative entropy that you can define over this A. But once you manage to do that, we have this strategy, which is like a puzzle, and it has 5 pieces. And the piece in the middle is defining the conditional log Sobolev constant that I just told you. The piece outside is having some form of decay of correlations on the Gibbs state, which I spoiled you here, that is going to be something of this form. And once you have these two notions, you have to prove 3 different things. First of all, you have to prove a result of quasi-factorization of the relative entropy, which is what is going to allow you to go, from the relative entropy here to the conditional relative entropy here. So essentially, this will allow you to go from this term to this term. Then you have to prove some geometric recursive argument, which is going to allow you to obtain the multiplicative term depending on A that you have here. And then, of course, you will have to prove that these 2 things are positive, in particular that this one is positive. So you will have to prove that the positive conditional log Sobolev constant is positive. Okay, so this is essentially what we do. We have a strategy. Right now, I guess it's a bit abstract because it's just a collection of pieces from which I'm giving 0 information. But then we have been using this strategy for certain different examples. And I'm going to skip it now because I don't have time for that. I just want to tell you that the results of quasi-factorization are inequalities of this form. So essentially, they allow you to reduce the relative entropy in a global lattice lambda to some conditional relative entropies in overlapping systems and some multiplicative term that measures how the correlations decay between the complements, so between A and C. And this is the key ingredient for this kind of results. So with this, we could prove at the beginning some simple example in some sense, which was when there are no correlations whatsoever. So when we have some tensor product fixed point, sigma, so sigma was just a tensor product everywhere. And then in this case, the proof was sort of easy, but this is how, following step by step of the puzzle, we could put all the pieces together and then prove that this semigroup had a positive MLSI. And this is actually quite interesting because this is modeling the generalized depolarizing semigroup. So that means that this is pretty useful to prove it like this. And then, all these blue things are results of quasi-factorization of the relative entropy, which led to some orange results, which are just results of positive MLSIs. Of course, I won't go into details here. But the last thing that I want to mention is this result in 1D. That is the most recent result we have in this direction. And it's the most useful so far. Because now we are considering Davis generators, so we are considering generators that appear very frequently in the physics literature, right? And generators that are really feasible. And what we are proving for them is essentially that they always have a positive MLSI, which now is not constant, but depends logarithmically with the system size. But this is good enough for us, because if this is something that only depends logarithmically with the system size, and we put it here, we still have something here that depends polynomially with the system size. So this is good enough for us. This means in particular that in this setting, for every positive temperature, which is the important thing here, our generator always has rapid mixing. So we have essentially Davis generators converging to Gibbs states of local finite range commuting and translation invariant Hamiltonians. This always has rapid mixing. And the proof just follows the pieces of the puzzle that I was mentioning before. Of course, this is very involved. I'm not going to discuss it here. We can discuss it later with someone in particular if you have some concrete interest on any part of the proof. But let me just mention that one of the key points of the proofs is that you have positivity of the spectral gap, and then you lift it to positivity of the MLSI just by paying a price which is of order logarithm with n. So order logarithm with the absolute value of the, logarithm with the size of lambda, So that means essentially that what we are doing here is take Castoriano and Brandau's result from 2016, where they proved that there's a positive spectral gap independent of the system size for every temperature, and then we lift it to MLSI just by paying the price of logarithm of the system size, which we said that is enough. And we can discuss the proof later, but I prefer to tell you some consequences of this result in 1D, which have to do with the fact that, okay, we have rapid mixing for every temperature for these Davis generators, which means essentially that the mixing time is not changing in a scale with any temperature. So that means essentially that there are no dissipative phase transitions with respect to when changing the temperature with respect to the mixing time, with respect to the convergence of the mixing time. Also, in the context of symmetry-protected topological phases, we have some consequences, which essentially is that, well, for every positive beta, 1D SPT phases thermalize in a time that is logarithmic with the system size, so with the size of lambda, even when the thermal bath is chosen to be weakly symmetric. And this is something that is very important because I know that people here work with SPT phases. Our results do not apply in the presence of strong symmetry. This is something that is important to remark here. And finally, these are consequences that our result has in 1D, but you might be wondering, I was talking about error correction before, so I guess you would like to have these kind of results in 2D, for example. And these are some of the things we are doing now. So first of all, let me just summarize. We have been discussing quantum dissipative evolutions under mixing times, for which we have used log Sobolev constants and decays of correlations. And well, we haven't shown a lot of results of quasi-factorization, but okay, we can discuss this later if you're interested. And there are many open problems, but the one that I was particularly mentioning is this one. Like, okay, if we have these results in 1D, can we do something similar in 2D and now for the quantum double models? Because this would be really interesting for some applications related to not having error correction. So with all of this, I want to conclude by thanking you for your attention and by thanking all my collaborators in these projects for their help. And now I will be happy to take your questions.
Much for the fascinating talk. Are there any questions? Okay. Start here. Go ahead.
Hi. Thanks for the very interesting talk. So I have two small questions. So one is you briefly mentioned that in these Davis generators, in principle, these generators they don't have to be local, right? So you can actually have non-local Davis generators.
Yes.
And is the locality important? Because in one of your plays, when you define the conditional relative entropy, you somehow have to sort of restrict your generators to be local.
Yeah.
I'm not sure if I missed that. And then the second question is, this all makes sense to me sort of in an intuitive level in one dimension, but then in two dimension, this mixing time can be very subtle, right? Because they can be different. Even if you have a positive spectral gap, in principle, you can have two mixing time. One is sort of like this metastable mixing time. The other one is sort of, the real mixing time, which take you to the finite system equilibrium states. So I wonder whether your sort of consideration can distinguish these different time scale, or it's the most general sort of complete convergence to the steady states.
Okay, so thank you very much. Very, very interesting questions, both of them. So first of all, for the first question, you were asking about the locality of the generator. That's essential for the proof. There are many, many steps of the proof in which you really need everything to be local. But I mean, every time, the thing is that maybe I didn't emphasize enough, but the Gibbs state we're considering here is a Gibbs state of a Hamiltonian that is commuting. That means that the generator you're obtaining is local directly. So that's something that is essential. Even when we have something non-commuting, we are not even able to prove that it's quasi-local or anything like that. With quasi-locality, it would be enough. But that's essential for the proof. So I agree with you that in general, Davis generator could be much more general. But yeah, this is not something that we can do. And for your other question, yeah, that's a very good question. This is something that we are not taking into account right now. We are just considering this definition of rapid mixing and this mixing time. And we are just evaluating everything together. But yeah, that's something that we could try to consider. So I will have it on mind. Thanks a lot.
And maybe one more quick question.
Thanks, Angela, for the very nice talk. So I was wondering this mixing condition and the equivalence between mixing condition and the boundedness of relative entropy. So you are looking at the other direction, right? Something like Pinsker inequality.
Yes, you mean to try to reverse the scheme here?
Mm-hmm.
Yeah, this is something that would be essential from my point of view, it would be essential to be able to reverse these arrows in some sense. Because then you would really have like some criteria to separate different forms of mixing times. So then you would have some criteria to separate when you are given a Hamiltonian, if this is good for error correction or not. And this is something that actually for classical spin systems, this happens because essentially in classical spin systems, everything is equivalent. So, but what we really expect is that in quantum systems, you have some more richness. So you have some real separation between these different forms of decay of correlations and different forms of convergence of mixing time.
Mm-hmm. Okay, thanks.
Thank you.
Thanks very much. Let's thank our speaker again. There you go. Thank you.
Next one.
Give it this. So Yanis, I think you have to use this one. Okay. Yeah, I think we're gonna.
Let's see which one.
Okay, our next speaker is Yanis Notzel. Yanis completed his PhD in Technical University of Munich. Then he did a postdoc in Barcelona with Andreas Winter. And later he led a transfer of academic results to practical implementations in the 5G lab of TU Dresden. And now he's leading his own group at TUM